Hello, everyone. My name is Chao. Today, my colleague Elise and I will be talking about a project named Factory Age Appliance. Both of us work for Seagate Technology, and this project aims to improve Seagate's manufacturing process by enabling machine learning technologies in our factories. With collaboration, support, and high-performance computational hardware powered by our great partner NVIDIA, we have successfully implemented a use case in this machine learning platform, which brings us great values and will be in full production environment by summer this year. This is a colorful slide, and now let's talk about a little bit about our company, our mission, and our goal. Seagate is a company focusing on providing data storage solution. Our motto is data is in our DNA. We craft the data sphere. We help maximize humanity's potential by delivering world-class, precision-engineered data solutions developed through sustainable and profitable partnerships. An IDC report published in 2018 predicts that the global data sphere will grow from 33 zettabytes in 2018 to 175 zettabytes in 2025. The big data era is not just coming, it's arriving. As people start saying data is the new oil, extracting executable actions that leads to actual revenue profit out from data become more and more important. Thanks to the rapid advancement in machine learning technology, in computational hardware development, and in software infrastructure revolution in recent years, now it is possible for us to build such a automated, data-driven pipelines in our factories to make reliable decisions in the manufacturing process, several millions of times a day. As a manufacturing company, Seagate generates numerous data every day. It has been a great challenge for us to get more value from the data. To better address the challenge, Seagate formed a group named Operations and Technology Advanced Analytics Group, or OTAC, a few years ago. By the way, both Elise and I are working as data scientists in this group. As a centralized data science group, where there are many other data scientists working within certain functional teams in Seagate, we assist any organization inside of Seagate who is interested in getting more value from their data. We help embed many types of analytics from descriptive visualizations to prescriptive and cognitive machine learning algorithms into other groups' processes. As a relative independent group, we also help to bridge technical and political boundaries by working between organizations wanting to improve their insights using data outside of their functional areas. We also identify new analytic tools and methods and manage POC or proof of concepts and pilot integration projects. This slide shows the high-level overview of Seagate EdgeRX, the smart manufacturing platform in Seagate factories we're building. The ultimate goal is to build edge analytics in the factory so we can enable real-time artificial intelligence and machine learning capabilities in our factories. The system is built on a convergence of several ideas. Concept of Industry 4.0, software architecture such as machine learning as microservices, Docker containers, and Kubernetes clusters. Breakthrough in machine learning technologies such as deep learning frameworks, as well as high-performance computational GPUs powered by our partner NVIDIA. First of all, our efforts are inspired by the vision of Industry 4.0, where computers, data generators, and action executors are all connected and communicate to make decisions without or with least possible human interactions, ultimately make the smart factory possible. The rapid technology advancement in machine learning, computational hardware, and software infrastructure make it possible for us. to build such an edge analytics system in factory that makes us one step closer to smart factory manufacturing. Now, let's talk about one of the specific challenges Seagate is facing today and how a real-time analytics system can help and benefit us. One of the challenges Seagate is facing today is that our factory produces billions and billions recording transducers per year. Our machine learning and artificial intelligence lab projects consistently show entitlements of such automatic algorithms. The challenge is that how can we implement such algorithms? How can we scale a low latency machine learning inference? There are three major challenges we need to address. One, high data volumes. There are millions of images and thousands of factory tool sensors we need to address in our factories every day. And second, we need to address the long latencies and bandwidth cost if we ever choose to use public cloud analytics tools. Secondly, the last, we need to meet our needs, our factory demand for real-time analytics. The solution we propose is to apply machine learning to transducer images and sensor data to find anomalies and defects earlier and reliably. In such a system, there are three major components. The first one is a fast storage array that Seagate builds, Nitro. Seagate has this all-flash storage array for training and actual raw factory data storage. Second, we need high-performance computational hardware, which is NVIDIA GPU, powered by NVIDIA, of course, and open source software like TensorFlow. The last one we want to build is a real-time inference at the edge. That is possible once we use the latest software infrastructure like Kubernetes, Docker containers. Combine these things together, we can get benefit of this system, including reducing test time, increasing efficiency, and improve throughput in our factories. So that can lead Seagate to have reduced bandwidth cost, to have faster test cycles, and to increase factory utilizations. So far, we have briefly introduced our company Seagate, our group OTAC, and our partnership with NVIDIA. We also gave a high-level overview on the edge analytics system we are building. Also, we introduced a specific application in the system to solve one of our challenges today. Next, my colleague Elise will get into more details about the project and the technologies we used to enable such a solution.
Thank you, Chao, for the great background. My name is Adis, and in the next few slides, I will use a specific use case to demonstrate the typical machine learning workflow we use to deploy smart applications at our factories. Our global operation of creating hard disk drives starts by producing over 100,000 read-write heads on a wafer. Each wafer is about 200 millimeters in diameter. What we will refer as slider is what contains the recording transducer. We produce more than 1 billion recording heads per year. Slider trailing edge inspection is the application I will be using for the purpose of this presentation. As I have shown you previously, this recording head is one of the 100,000 on a wafer. This particular side of the recording head goes through a number of tests. And these tests leave behind some electrical traces and remnants like this, which are not defects, and we are not interested in identifying this. But there could be other defects on this surface that needs to be identified that would affect the application of this particular recording heads. We do 100% inspection of our recording heads, and this is done in very large clean rooms. And the process of doing so manually especially have a number of issues that comes with it, and that one of that being that it leaves a large clean room footprint. And if it is done by human operators like we see here, then it is susceptible to human error defect misses, and humans could actually introduce another form of defects in the form of contamination to the recording heads. In order to alleviate the challenge with human inspection, we look into a possible approach. And one potential approach is automated inspection, rule-based, that's programmatically based approach. In order to do that, we start by collecting data. In this particular case, our data is an image kind, and we segment each and every part of the image. And we create for the different segments we create a template for that and define regions of interest. And within each regions of interest, we define different rules that identifies whether a pixel within that region is good or defective. And then we test this set of rules that we come up with on our sample data set and see if it can capture the good data and the bad data. And if the need arises, we create a new rules and test it, and we optimize, repeat the process until we come up with a set of rules that captures the defects on our image within the accuracy that is acceptable. The challenge with this approach is new designs would require new templates and new regions and new rules to be defined. And it also requires experts of computer vision to develop these particular regions and rules for each and every single kind of defects. And even if a defect is of the same type, if it is in different region, that needs to be defined and captured manually again using a specific set of rules. The rule-based approach we just discussed requires feature definitions for each defect type. But the question we want to ask is, can we automate the feature extraction process? And for this, we turn our attention to supervised machine learning. In order to do that, we start by collecting large data set. This sample of data set would contain both good and defective images. And we use markup softwares to label each pixel as good or bad, or that's defective. And we would train a large neural network to extract these features from the labeled data set automatically and learn the patterns within the image. And of course, this process by itself requires a lot of optimization until we come up with a model that has a great accuracy on a separate test data set. And new designs and process variations, even with this approach, would require creation of new models, and that is new training. And once the model is established, new training can be completed by subject matter experts. And one of the very interesting thing about this, in addition to extracting the features automatically, is the accuracy of such models typically grows with more data, especially if there is enough variation with the training data set. And 3 million image inspection of 3 million images per day in such automated manner leads to multi-million-dollar savings per year. Here I will briefly go over the model that we use for our application at hand. For this particular application, it was not enough for us to identify an image as good or a defective kind. Rather, the task at hand was to know if an image contains a specific kind of defect, where that defect is, and what the size of that defect is. So we had to do a pixel level classification. We have to identify each pixel level as good or as belonging to any one of the defect classes. And in order to achieve this, we looked into segmentation models, specifically with the encoder-decoder kind segmentation models. The encoder-decoder kind, the encoder part of this model captures the context, and we localize very precisely using the decoder part where that context is. We started by looking at UNet as a potential model, but UNet did not acquire the accuracy level that we wanted, and this is mostly because we did not have enough level dataset where UNet uses the raw dataset as an input, and without enough level dataset, it was not able to capture the complexities of the image that we've seen previously. So we moved on to leveraging another kind of model, an encoder-decoder kind, which is Segnet. Segnet is really like UNet, but what makes it differ is that the first part, or the encoder part, uses transfer learning. And transfer learning is a machine learning technique where a knowledge gained while training one model to solve a given problem can be applied and used to solving another but related kind of problem. So in this case, the first part of it for the encoder part uses a pre-trained VGG16 model. So we would load the weight of the pre-trained model and then train the entire model on our data set. This yielded a very good accuracy and acceptable accuracy level for our model, and we will see the examples of how accurately it was identifying the different defect types. We also have tried mask RCNN, which again uses a transfer learning on pre-trained model. The pre-trained part here is ResNet 50. And it also yielded a very decent result, but upon inference, it performed way slower than Segnet. This is the reason we stuck with Segnet, because it provided good accuracy and relatively higher throughput than any other model we tried. So how does it look like for our application? Segnet actually yielded very high accuracy for us. So this is one specific kind of defect types, which is sort of a contamination here. And we do, of course, we start by creating a mask, and that is a sample data set, right? So for a contam, this is the actual defect, and this is what was identified as a defect. Another kind of defect classes that Segnet really identifies well for us were what we call wafer defects, which resulted during the wafer production process. And these are defect classes or types that appear on the bond pads. And again, these were captured really well. The third kind was chips. So that's the chipping of the bond pads. And depending on the position, the chips are named differently. But the chipping could be on any end of these bond pads. And these were also captured very well by Segnet. And wire bonds. Again, these were also captured using Segnet. That was a very brief summary of our modeling process. Next, we will discuss the modeling deployment workflow that we follow. We use Keras to come up with a training model with a TensorFlow backend, and the model would end up in H5 format. And this H5 format is then frozen. And the freezing process is to eliminate any unnecessary variable nodes that are not used for the calculation of the output that we're interested in. And those are replaced by constants, and subgraphs, again, of unnecessary to calculate the output are also pruned. The next step is to further optimize our model. This time we use TensorRT Inference Server to accomplish that. We work very closely with our great partners at NVIDIA to optimize our model. And we're converting the floating point 32 to floating point 16 so that at a lower precision we can do fast inference on GPUs. We use TensorFlow serving and TensorRT Inference Server, TensorFlow serving from Google and TensorRT Inference Server from NVIDIA as inference servers to deploy these models. In our model deployment workflow, the last step was using inference servers to organize our models. The main reason that we use inference servers is it's the most efficient way of using our compute resources for inference. Inference servers, they allow us to host models across different hosts or a single host of the same GPU, and inference can be done concurrently across these many models deployed within the inference servers. And with inference servers, easy model management is available. And what we mean by that is without stopping the server and without interrupting the inference, we can load and unload models. And inference servers, in this particular example, TensorRT Inference Server from NVIDIA, it supports multiple model types, including TensorFlow, TensorRT, Saved Models, GraphDev, and many more. And it can run in a single GPU environment, or it also supports a multi-GPU environment. And sometimes models are created to actually process images as they come individually with just a batch of one. But inference servers allow a server-side queuing and batching. So in addition to concurrently performing model inference, we can also queue and batch the incoming inference request using inference servers. And on top of all of this, we can remotely monitor the health of the inference server, hence the health of the models that are hosted by the inference server. Here is a summary of our deployment performance comparisons using different inference servers. We have tested TensorRT Inference Server from NVIDIA and TensorFlow serving from Google. And this is a per image time for inferencing. So with the pre-processing and inferencing on a given image, it takes up to 240 milliseconds per image to do a segmentation, a pixel level segmentation of 5 classes. And using TensorFlow serving, it takes up to 360 milliseconds. And TensorRT Inference Servers, where TensorRT optimization on the model is done, reduces the time to only 180 milliseconds per image. And this difference could be significant when we think of it over 3 million images that needs to be processed per day. So this is a brief summary of how we do our modeling and how we do our deployment. But it is very important that the process we follow is scalable, especially when we think of needing to process over 3 million images for this particular process. And this drive manufacturing process requires hundreds of and thousands of processes before this drive emerges. For this application, a proof of concept was done using a few thousand images, and commercial software, Cognex VD, and Segate-based TensorFlow model. Both yielded great models of the same level or better accuracy as the human inspections. And both training and inference for the proof of concept was done on workstation GPUs. But our application at volume in our manufacturing factories requires to handle up to 3 million images per day. So very robust inference and model management is a requirement. And deployment at scale is very important. And the system that we would be deploying this at scale should be very flexible to handle applications and manage applications easily using inference servers. In order to achieve this scaling to production, we designed and built a scalable Kubernetes orchestrated GPU and CPU cluster. And this cluster is what will be further explained and in detail presented to you by Chao in the next few slides. Thank you.
In this slide, I would like to give a high-level overview on our factory machine learning platform. Our client, manufacturing factory, would like to send some data, an image in this case, to such a system, such a platform, and to receive a signal saying they should pass or fail the image they just sent. The system are consisted roughly by 3 major components: a training server, a fast storage array, and an inferencing server. So how does this system work? First of all, our group OTAG would work with a functional group to identify the problem, to pick up, to collect the data set, and to pick up an appropriate algorithms, and we train a certain model on the data set and validate and test them. Once done, we would push the model to the model repository on the storage array. Also, we would design our pre and post process before and after we apply the model into Docker containers, and we push the Docker containers to the fast storage array as well. Meanwhile, the factory would send the raw data, slider T images in our case, to this storage array so that the inference server can pull the model, can pull the Docker containers, and can process the images. Of course, we might generate some middle results during the machine learning algorithms, and we can save those middle results in the storage array as well. And finally, the inference server combines those things together, inference the image that was sent by the client, and then give the client a result. So there are 2 notes I would like to take here. One, NVIDIA GPUs are included in both training and inference system because the GPU is a very powerful training machine for deep learning models where we use most. They're super powerful, and with that, we can achieve our response time and the throughput requirements in manufacturing. And those GPUs are powered by our great partner NVIDIA, of course. And another note I want to make is that we have a rule-based classification system at the end of the final step. Why? Because we want to have interpretability and flexibility. So for interpretability, we all know that deep learning, while efficient in doing its job, it is very challenging to explain why it did that, why it did those. So to make our manufacturing team and engineering team saying that, make them comfortable of using this system is that, okay, see, this is how our algorithm did that and why we classify our incoming images as a pass or fail. So that they can easily see by saying we did the segmentation and we mask the area of the defect and given the type of defect, so that they can easily see how the system works, whether right or wrong. Another reason is flexibility. So in manufacturing, even for the same images, if we used the part which generate this image into different products or use them following by different process, we can have different specs. So one slider cannot used in one product or one process may be able to be used in another product. So if we use one single machine learning algorithms for all of these things, then we have to train many, many models for different process or any requirements change in the manufacturing, which is very inconvenient. If we have our rule-based classification system at the end, then it can easily say, okay, for this one, we really need to reject it because this defect is super important to our downstream process. And for this one, since we adjust our downstream process, we have more tolerance of that. Maybe we can just pass them on. So to have rule-based classification system is really important in our system so that it can provide the required flexibility and interpretability to our customers. Now let's get a closer look of Seagate HRX, the machine learning platform in Seagate manufacturing. The green box is Seagate HRX system. As we mentioned earlier, there are three major parts. The first one is a training system. It's HPE Apollo 6500 configured with 8 NVIDIA V100 GPUs. For the storage array, we have Seagate Nitro FFA. We have Lightning speed that enable our high performance system. And then we have a inference system, HPE Edgeline 4000, configured with 4 NVIDIA P4 GPUs per unit. So how do we make use of this platform? At the very beginning phase of the project, our group OTAG works with functional teams to define the problem, to pick up the right algorithms, and to train a model and then validate and test it. We go many iterations until at some point we are confident enough and the model and the corresponding process are mature enough so that we put things all together in the edge system and we transfer the technology or transfer the whole pipeline to the operation teams in factory. So the operation team in factory, they are responsible to all the actual factory operations. So they are actually capable and they need to assess the training service because they know their data eventually the best. So they can use the training services that we designed in the edge system to fine-tune certain parameters. They're not generating any new kind of model, but they can fine-tune the parameters to best fit their need in the training system. And once they are satisfied, they can push the training system into the inference server so that the manufacturing process can access them. So in the process, they generate a lot of data, of course, and the data is then pushed to the, through the storage service to the storage array in the Edge RX system. Once they are pushed, the factory can make a request to the inference service saying, we have this data and please give us a signal saying, how do we do to the next steps? So then there is action coming back from the inference service to the factory. So this is in general how this system works. And on top of that, we also have a feedback system. So we have actually a monitoring service looking at the Edge RX system itself. It also looks at the results coming from the inference service. So if there is any abnormal behavior we are not expecting, or the system goes in some abnormal status or is just failed, it will raise factory alert to the operational teams, and it will also alert us, like say there's something wrong going on over there. We need to take a closer look. So there are a few notes that I want to mention. The RX system is managed as Kubernetes clusters so that we can easily scale up or scale down, mostly maybe scale up the system to meet our needs. All the services are containerized, running on Kubernetes. That makes scaling up and down super easy. And the last one is what I have mentioned, because the operational team is the team that finally responsible to the manufacturing operations. So they actually have certain access, and they can fine-tune the model, and they actually monitoring the results and give us the feedback if there is something goes wrong. In the next two slides, I'll talk about the detailed implementation on the application architecture. As you can see in this client-side slide, we have a message broker. So this is one of the key components that we use to decouple the client and the server side. So in the client side, it only needs to talk to the message broker through a REST API server. And the REST API server is running as a Kubernetes service deployment on the Kubernetes clusters. Also, there is a Kubernetes volume database that contains all the data, middle results, as well as reports that can be read by a visualization and analysis web app deployed as a Kubernetes deployment and can present the visualization results to the client. So when the client has some data to be inferenced, the client would push the data first to the Kubernetes volumes, and this Kubernetes volumes is shared with the client, server side, of course. And then the client would send a message to the REST API server saying, those are the list of images, for example, 1,000 images that I need the results from. The REST API server will then split the messages into smaller messages and send, based on the model they picked, they send them to the different queues in the message brokers. Now let's take a look at the server side. In the server side, we can host many different models, and each model would have its unique deployment. Kubernetes deployment contains corresponding pre- and post-process code. So each model deployment would listen into a message queue. If the queue is not empty, the deployment would grab the information from the queue, pull the corresponding data from the Kubernetes volumes containing the images, and do certain pre-processing, and then make a call to the NVIDIA TensorRT inference server. Once the results coming back from the TensorRT inference server, it will do certain post-processing on top of it and send the results back to the message queue. And how do we design the architecture for the TensorRT inference server? So we did in such a way. So first of all, remember that we have a Edgeline 4000 as our inference server, so we have 4 GPUs in one unit. What we did is that we deploy a TRTIS TensorRT inference server. It's containerized as a Kubernetes deployment to each GPU. So we have 4 GPU, so we have 4 of such Kubernetes deployment for TRTIS. And these 4 deployment are organized or are covered by a load balancer. So any of the GPU inference call goes into that balancer, and that balancer will evenly spread the load into these 4 TRTIS deployment. And the model, or all the models, are stored in the Kubernetes persistent volumes that is attached to the TRTIS. So we can store as many models as we want, and we don't need to worry about queuing them or make a certain call to one of them and load it to memory and then release that. TRTIS will do all the jobs for us. So this is the overall architecture for the server side. There are a few notes. First of all, the message broker, as we mentioned before, is used for queue requests from clients, which decouples client to the server. Secondly, the number of TRTIS pod equals to the number of GPUs, which leaves TRTIS handling inference call to multiple models, and we don't have to worry anything about it. If we got a new model, we just need to push the model to the persistent volume. If we want to retire a model, we just get rid of it from the persistent volume. And we don't need to worry about all the memory management, all those kind of stuffs. So we store all the models in the Kubernetes persistent volumes. And the last point is that we separate service allows adding, updating, removing models from deployment upon approval. So each model has its unique deployment. So if we want to add or remove the a model, we just need to go ahead and deploy a new pod corresponding to that model, or remove the corresponding pod or deployment. So that's the way how we design the server side of the system. Summary. So far, we have introduced Seagate Edge RX system, how it was architectured, how is our first use case implemented in such a platform, and how the application architecture was designed. Overall, Seagate has embraced machine learning and edge computing to optimize the manufacturing process. In the first use case, deep learning approach are used. In fact, they are being used and explored for many more applications at different stages of drive manufacturing with the goal of enhancing our smart manufacturing. We introduced our platform here, and one use case, but we have many more use cases to be deployed and implemented inside the platform. Last, Seagate Edge RX, scalable Kubernetes orchestrated GPU cluster serving as machine learning platform, is being deployed at our factory worldwide to realize that goal. We have quite a few factories worldwide in different locations, and we are deploying this platform in every and each factories so that we can make use of machine learning to enhance our manufacturing process overall as a whole. Thank you very much for our presentation, for listening our presentation. If you have any questions, please do not hesitate to contact us through our email listed in the introduction page. Thank you.